Hi, so this video is about file systems and how your file system stores your files on a disk or an SSD. And in particular, I wanted to talk about inodes. Inodes is the underlying structure that's used by Unix file systems to store files. What's amazing is that I'm currently restoring a Unix file system from or a workstation from 1983, and it uses much the same structure as you see in a modern Linux system based on inodes. It's a good system. It's very compact. It's fast. Lots to recommend it. You may have heard of inodes if you've been around file systems in Unix for any time and nodded sagely to show how wise you are, but perhaps not understood or perhaps you're not even known how do they work under the hood. So that's what I want to talk about today and dive into the details of the bits and bytes of how inodes work, because it's kind of cool. Start off with a disk is you have a disk which has a large amount of storage, and you have some files of variable length, and you want to be able to store them. So you need some sort of system to be able to manage where those files are put and be able to retrieve them later. While that's not the case with SSDs, with disks and sort of those spinning disks that we used to use, the geometry of the physical location of where your files are stored is based on tracks and sectors and cylinders. But to make things simple, often in terms of on file systems, we just talk in terms of logical block addresses, and it's a number that goes from one to a big number, and the mapping of that logical block address to a physical location on the disk is something that's the low-level driver does, and we don't need to be concerned with. We just say, go get block 423, and it goes off, and it may be on a particular cylinder, maybe on a particular sector, maybe on a particular track. We don't need to care. So okay, so when you create a file system, it needs to create a large pool of these inodes, and you have one inode at least for every single file in your file system. So when the file system is created, you create a massive pool of many thousands of these file descriptors, and as you create or copy in new files, it takes one of those file descriptors and allocates it, and that's the way, that is the sort of top level structure for finding all the parts of your file. So if we just look at this is the inode struct for a Tektronix running from 1983. And again, it's really interesting that it's really very, very similar to what a modern Linux inode will look like. So you can see here that I've got various things like the mode, I've got permission bits, I've got a link count, so that if you have hard links and you have two files pointing to the same physical file names pointing to the same physical file, you have some ownership bits. The interesting thing here, though, is as far as understanding inodes and how they work under the hood, is this part that's called FT block. Now, those logical block addresses in this particular system use 3 bytes. In other words, it's a 24-bit number, which obviously limits how big a file system you can have. A modern file system will use a much larger address. This is from 40 years ago, and that was ample for the time. But the important thing is that the structure and the way the inode works is very similar to what it does even today. So if we look at a sort of layout of what that block, those 13 blocks. So these 13 blocks here, for example, that we've got, each with, it's a 3-byte, so the logical block address is 3 bytes, and there's 13 entries. So what those 13 entries are is this. The first 10 are direct blocks. So they allow you to go and get the logical block of the address of the first block, and you can ask the file system to go get that block, and the first 10 are just direct. And so that means you can access extremely quickly, without any indirection, a file of up to 5,120 bytes. So it's 512 byte blocks, and there are 10 of them. Again, a modern file system will have much bigger blocks, 4K, bigger than that even. The next entry in that array is the what's called single indirection block. And what that is, it's a logical block address that points to a block of 128 logical block addresses. So with a single indirection, you can go and fetch that block, and in that block will be more logical block addresses that you can enumerate through. And that means in total, through a single indirection, you can get to 64K bytes of your file. If it's bigger than that, then you go to the next entry, which is a double indirection, which means it's a 128 logical block addresses that each point to another 128 block addresses, which then point to individual blocks which actually have real data in. And that means that with a double indirection in this scheme, you could store up to an 8 megabyte file. So you can enumerate all the blocks that make this file through that double indirection. And if it's bigger than 8 megabytes, which again, for the time that this particular file system is from, would be unusual, that we didn't have files that were much bigger than that. But then the last one is a triple indirection, and that is a 128 logical block addresses that point to 128 logical block addresses, which point to 128 logical block addresses, which gives you an addressable range of 1 gigabyte. And that is, in this system, more than sufficient for the kind of size disks that were seen at the time. A 100 megabyte disk was considered quite large back then. So while the sizes of these blocks and the number of indirections changes, obviously in a modern Linux system, this scheme is largely how systems work even today. Now, one thing you'll notice with these file descriptors, if I go back to this struct inode, is there's no mention of file names. This is just a file descriptor which has no name associated with it. And it just is a mechanism for determining where on the disk all the blocks that constitute that particular file live. Okay, so you might be asking, okay, so how do you do file names and directories? Well, it's kind of a neat system. So file descriptors, as I said, they don't have any file names associated with them. They are just an entity that says this is a file and this is a collection of blocks. But that mode field in a file descriptor is important, and so in particular, if you look at in this particular system, and it's a similar system for a more modern file system, is that you can have file descriptors which are marked as, in this case, ifreg, which is a regular data file. It's it's got a bunch of data, or you can have them marked as a directory file. There are other modes as well, such as block devices, character devices, pseudo terminals. Just setting those aside for now. And so the idea then is that if you have a protocol, a requirement that, for example, the very first block file descriptor points to a directory file, and directory files, they are data like any file, but they have a particular format. In this particular file system, the format is that each block has a small struct of 16 bytes, which is a file descriptor number, and a name, and that name is a file name or a directory name. When you have, what's kind of neat is that, a common thing with high performance software engineering is you want to have something which is um, uh, always dealing with the same size objects, and yet we can have file names which are very long, we can have file names that are very short. You don't want to go for the lowest common denominator of having, a structure that can take up to, 1,000 characters. So in this particular file system, what they opted to do was to say, okay, well, the large majority of files are going to have file names which are less than, I think this is 14 characters. When we see something which is longer than that, then we can just create dummy entries in the directory file to create large file names. And so we don't compromise the size of our directory entry for the small number of cases where you have very long file names. But what this means is that I can pick up that very first block, and I know that this first block in this particular file system will always be, it's the root file descriptor that is a directory file, and I can enumerate all the entries in that directory file. Some of those will point to file descriptors which are files, and some will point to file descriptors which are themselves directories, and I can recursively descend that, and in that way I can enumerate all the files on the system. And so it gives you an insight, I guess, into when you do ls-l, for example, there's actually quite a lot of work that's going on behind the scenes of reading those inodes and then indirecting through them to, one, get potentially the file contents, but also to get all the other statistical stats and permissions information around a file. So that's it, really. I just thought it'd be an interesting kind of deep dive into how inodes under the hood are actually implemented, admittedly in the context of a very old Unix file system, but I think lots of the basic structure works very, very similar today.